All right, tonight we're going to be talking about hydrogen generation, hydrogen hazards, sources of hydrogen in reactor accidents. And this comes because of what happened at Fukushima. We saw there's always been at all nuclear power plants, especially boiling water reactors across the country, a concern about hydrogen generation. And that's because when we have a reactor and we have so we've got a reactor here and we've got a core, and change my lines up here. Clear that there. We've got a reactor vessel and we got the core inside here, and this has the fuel in it. These are all the fuel rods, and there's water in this reactor. So this reactor has a water level in it above the fuel. And the idea is that we want to make sure that that stays above the fuel, because if this water starts lowering, if this water level starts lowering, this fuel gets exposed to air. And we have a reaction called a zirconium steam reaction. So the fuel cladding is made of a zircaloy alloy, a zirconium. And if we take zirconium plus H2O, water, that gives us zirconium oxide plus hydrogen plus heat, and a lot of heat. So what that means, it's an exothermic reaction. It's exothermic, and it feeds itself, because what happens is, if as long as temperature of the fuel is maintained low, and what low is, as long as we're cooling the fuel, we're maintaining that fuel temperature about 544 degrees Fahrenheit, because it's a saturated system inside a boiling water reactor, which means as long as there's cooling, as long as we're removing heat, it stays at the saturation temperature for that pressure. And the boiling water reactor is about 1,000 pounds, a little over 1,000 pounds, but about 1,000 pounds. So with it above with it at about 1,000 pounds, that saturation temperature is 544 degrees. That's normally what all this fuel, the temperature of the fuel. If we start removing the cooling, if the water level starts dropping and we remove the ability to cool, that fuel, we're not removing the heat, starts to heat up. And any time we get at above 1,200 degrees Fahrenheit, this reaction starts happening, and it produces hydrogen and it produces heat, and then it gets hotter, and it's exothermic, and it's feeding itself, and then the fuel gets hotter. It gets to 1,400 degrees and it gets worse, and 1,600 degrees and gets worse. And what we know is that at 1,800 degrees Fahrenheit to 2,200 degrees Fahrenheit is where it just takes off. It rapidly accelerates. It just really, really takes off. So that contributes additional heat besides the decay heat, besides the intrinsic heat from the sensible heat from just the high operating temperature, higher operating power for so long. So the temperature of the core goes up, and that produces large volumes of hydrogen gas. Now, hydrogen gas is flammable and potentially explosive. We're going to get to that in a second. But that's not the only source of hydrogen in a boiling water reactor. We also have the radiolysis, so the radiolytic decomposition of water. Now, this is negligible under accident conditions, but what this means, clear this off for you, is we have H2O, oxygen and hydrogen. So this is a hydrogen, and this is a hydrogen, and this is an oxygen. Guess the two doesn't make sense there, does it? And we have a neutron. And this neutron comes cruising by. Now, the neutron comes from the fission that's happening inside the reactor. The fission is happening, and it's releasing 2 to 3 neutrons per fission event. And these neutrons are really high energy. They're traveling really fast. So a couple of things can happen. One is a neutron that hits a hydrogen atom, which is about the same mass, suddenly slows down the neutron. And that's what we call thermalizing. It slows the neutron down to the point where it is at a lower energy level where it can cruise by a big uranium 238 atom atom and get absorbed. And that's what causes another fission. Well, in imparting its energy to that hydrogen atom, what it can do is it can break that bond with the oxygen and knock that hydrogen loose. So as we're going through, as this fission is happening inside the reactor, these neutrons that we're thermalizing is creating hydrogen. It's starting to break these bonds. And it's not just creating hydrogen, it's also creating oxygen, because these hydrogens get knocked loose. And then we have oxygen, and these oxygens pair up. And so then we get O2. Now, what's really bad about having oxygen inside a big metal container is oxidation. And if we have oxidation inside the valves, inside the pumps, inside the piping, any of the components of a reactor plant, that oxidation builds up oxidation products, just like iron rusts, and it builds up a layer of rust that can break loose, that can come loose. And so anytime any metal oxidizes, whether it's aluminum or steel or, any fancy metal that we use in a nuclear reactor, that oxidation layer can break loose. And when it breaks loose and it travels through the reactor, it becomes activated. And then we build up these products, these crud, and that's a formal industry term, CRUD, crud, that settles out in low spots and causes problems with high radiation levels. So anybody going for an RP tech, radiation protection, or rad tech, or health physics license, those are things you have to deal with, are these hot spots that happen inside the reactor. And so in summary here, we've got the loose hydrogen, we've got the loose oxygen, we got these neutrons that we've slowed down, and it causes the fission to happen. Now, let's clear this, and I'm going to confuse you for a second, because we also have something else going on inside the reactor. And what we have is gamma energy. This is how we draw gamma energy. And this gamma energy is radiating, and it's a very penetrating radiation. And it radiates through the reactor, through the metal walls, into the reactor building, through the drywall, into the reactor building. Like, this is the radiation that we're measuring dose for, because it's very penetrating, very high energy. What it does is it finds hydrogen atoms and oxygen atoms and causes them to join up. So it can cause the free hydrogen to combine with the oxygen. Now, what we want to do between the difference of having excess hydrogen or excess oxygen, the biggest concern is actually the excess oxygen. So way back at the start of, I've got a reactor here, and we got a steam pipe that comes out, and it goes through a turbine, and it goes into a condenser, and this condenser goes into a pump. Oops. Well, that was cool. And then we feed water back into the reactor. So this is kind of our cycle, and it's going this way, this way, this way. And then, of course, we got our core and the flow of water removing the heat from the fuel. So what we do is, around our condensate pumps, we have this bypass line. And this bypass line here has an injector valve on it. The discharge of the pump is a higher pressure than the suction of the pump. So on the discharge of the pump, which is this, oh, apparently I'm getting a, which is this here, this is the discharge, is at a higher pressure, and that pushes water through this bypass that goes around the pump. And in this injector, we have hydrogen. We inject hydrogen into this injector valve. And this goes through to the suction of the valve of the pump, and then it goes into the system. And so we're putting excess hydrogen into the reactor so that we so that we have more hydrogen available to bond with all the excess oxygen, so that it can so we don't have any fission. So we minimize the buildup of the crud. Am I making sense so far? All right. So other sources of the hydrogen, of course, is the radiolytic decomposition, but then the reactor itself is providing that feedback where it's combining the hydrogen, and then we're injecting an extra hydrogen in. So the hazards, the hazards posed by hydrogen is it's colorless, it's odorless, and it's highly flammable. If it's released in sufficient quantities, it creates a risk. And we saw this with Fukushima, where they had a hydrogen explosion. We're going to talk more about that in a second. So hydrogen isn't always explosive, though. It is flammable between 4% and 75%. So if I have a volume of space that has hydrogen in it, that hydrogen, if it's 2%, it's not flammable. And above 75%, it's not flammable, which is kind of a weird thought, right? If I could fill an entire room with hydrogen, this highly flammable gas, and it's 100% hydrogen, and I light a match, it's not going to burn because it's too concentrated. It needs oxygen. And what they found is that mixture here is if you have 4 to 75% hydrogen in a volume of air with nitrogen, oxygen, then it's flammable. And inside that, 13% to 60% is explosive. Oh, writing on my face, I picked the wrong. There we go. (13 to 60% is actually explosive. And so it's inside a reactor. It's, it's a water system. What's going to cause it to explode? It could be electrical arcing. It could just be a hot surface. It could be a static discharge. So the danger comes from if we let the hydrogen out of the reactor. If we, for some reason, let the hydrogen out of, we have the buildup of steam in here. We have a buildup of hydrogen. Hydrogen starting to form with the steam, and it gets out and it goes into the turbine, and it gets into our main condenser. And we have a main condenser. We take the air and non-condensable gases off of this main condenser, and we send it into the atmosphere. Now, we've got a big process before we send it into the atmosphere. We scrub it, we clean it, we let it sit in a holding pipe for a while to decay any radiological hazards. We send it through multiple sets of filters and everything like that. But what if we have a bunch of hydrogen that we're trying to get rid of? Well, we don't want to send the hydrogen that way. So we have our primary containment. We have the dry well that the reactor's in, and it's got a vent, and we can vent the hydrogen out the reactor to the top of the reactor building. Well, before Fukushima, all the plants had the ability to do that. But with Fukushima, they were venting hydrogen, they were letting hydrogen out, and they had a problem called deflagration, um, a rapid burn. Think of it as just a rapid burn, and then an explosion, and vent vent pipe didn't handle that explosion, and it blew the top of the reactor building off. So deflagrations and detonations occurred in units 1 and 3, destroying the secondary containment structures. So what we have now in all reactor plants across the United States, especially the boiling water reactors, is this piping for the vent is what we call hardened containment pipe vent. So it went from just a normal thin metal, regular metal pipe to a really substantially heavy duty, bigger pipe, so that it can vent the hydrogen without being damaged from the deflagration or the explosion. So deflagration, like I said, think of it as a fast burn. It's a subsonic flame that just goes through. If you've ever been around a campfire and somebody put gas on the campfire and then threw the match on it, and you get that whoosh is a deflagration. Whereas a detonation it's pretty obvious what an explosion is. So if you get that sweet spot of hydrogen, you get an explosion. Otherwise, you get a deflagration. So other things we do to control the hydrogen accumulation is we inert primary containment. And what that means is all this space in here, all this space, we let all the normal air out and we fill it with nitrogen, so that if there's a hydrogen buildup, if we have a hydrogen release into from the reactor vessel into secondary containment into the drywall, then we don't have a hydrogen oxygen atmosphere. That means that 100% of the combustible gas is hydrogen, because the rest of it's nitrogen, and nitrogen not combustible. So we have this filled with an inert gas. Now, right now, Columbia Generating Station is going through an outage. And in this outage, we have the drywall opened up. The reactor shut down and the drywall's opened up. We got a big manway right there, person way, and that lets people in and out. And we have air in there. So now we have the risk of an explosion if there's a hydrogen release. Let's see here. Hydrogen recombiners. Oh, and so let's go back and revisit real quick that loop where we inject hydrogen into the condensate system. So I got that pump down here, and we inject hydrogen into it here. Well, eventually, when the steam comes out and it goes through the turbine and it goes into the condenser, and we take all these air non-condensable gases off, this is going to have hydrogen in it. In fact, it's going to have a buildup of hydrogen because we put more hydrogen into the reactor, and we have that breakdown of hydrogen and oxygen, the breakdown of the water, the radiolytic decomposition. So this hydrogen, we go through a system called standby gas. No, that's not what it's called. Doesn't matter what it's called. And we inject air into this pathway. So we heat this up. There's some heaters, and we heat it up, and we cause it to, we get all the water out. So it's just gas. And then we inject air into it. And that air combines the oxygen, combines with the oxygen, and it's called the recombiner. So yeah, it's the oxygen recombiner, and we recombine oxygen with hydrogen, and that takes the hydrogen back down before we send this up through the stack. All right. So hydrogen in enclosed spaces. Read you my notes here on Fukushima, March 2011. They were Fukushima Daiichi plant at Unit 3. They were unaware that the reactor building was filling with hydrogen. The gas had migrated through shared piping and degraded seals after venting operations from the damaged reactor. So they had the reactor and they vented the reactor into containment. And they didn't know that they had exposed fuel already. So the fuel, the water level was down here because they didn't have all the instruments because of the earthquake, the loss of power. They were really operating blind here. And so the water level had gone down and they had all this fuel exposed that was getting hot. And this zirconium reaction was happening and releasing a lot of hydrogen. And they vented that into the secondary containment. There was no alarms, no smoke, no order. At 11:01 a.m., an explosion tore through the structure, and you can go to YouTube and see the videos of the explosion. They captured it live on TV. It was likely a detonation, and the concrete walls collapsed. Equipment critical to the response effort was buried or destroyed. 2 workers were injured in that explosion, and it delayed access to the unit for days. Which may have contributed to additional fission product release. So hydrogen is undetectable without instrumentation. It tends to rise and accumulate in high unventilated areas. In confined geometries like reactor buildings, it does not need a spark. Hot surfaces and static charge is enough to ignite it if it's in that range. The risk is compounded when the focus is on, hey, let's get some core cooling. Let's get more water into the reactor. The gas accumulation is kind of an out of sight, out of mind issue. So out of Fukushima, one of the industry changes beside the hardened containment vent is that hydrogen's no longer considered a low probability consequence because we saw it happen. We watched it happen live on television. So they've taken it a lot more seriously, and we talk about it, we train about it, and yeah. So the hydrogen generation during severe accidents poses a significant risk of explosion. The zirconium steam reaction is the primary source during core damage, and the risk escalates as cladding temperatures rise. So we want to make sure we have inert spaces. We want to make sure we don't have any sparking. In fact, we use AC motors, AC motor operated valves outside of containment, but any valves that are inside containment have to be DC powered because they're less likely to spark. And yeah, so that's what I wanted to talk about with hydrogen. The core damage is also a topic this week, but I did another video on core damage already, so hopefully you watch that.